Hi everyone, my name is Ben, and today I'm going to talk about the chemistry of coffee, as well as the chemical processes involved with decaffeination. So let's get started. Coffee is full of various chemicals, with over 1,000 aromatic chemicals alone. Chlorogenic acids compose the majority of the antioxidants in coffee, and we'll come back to that later. Before we go more in depth, I want to point out some biochemical properties found in new research. This research has identified that coffee increases the amount of glucose absorbed by cells by almost double. This may decrease blood glucose levels in the bloodstream and have an impact on type 2 diabetes. Another point of interest is the possible carcinogens in coffee. Methylimidazole is a known carcinogen formed in coffee during the Maillard reaction of browning, which we will also come back to. However, the amount is extremely low and considered safe. With that being said, current research into coffee shows people are less likely to develop liver, colon, oral, and esophageal cancer. It is not associated with an increase in mortality, and there is lower cardiovascular disease found in those that consume coffee. Alright, now let's get into some organic chemistry. Coffee is one of the richest sources of chlorogenic acid antioxidants in food or beverages consumed by humans. Chlorogenic acids form during esterification, which is a chemical reaction between two reactants that form an ester through an OH group being replaced by an O-alkyl group. An ester is a compound noted for having a characteristically pleasant odor. Specifically, transenamic acids esterify with hydroxyl groups on quinic acid, creating various chlorogenic acids of quinic. 50% of these chlorogenic acids degrade in high temperatures such as roasting, causing them to hydrolyze, dehydrate, or completely disappear. Maillard browning also occurs during this time. Maillard browning is a chemical reaction between amino acids and reducing sugars at between 140 and 165 degrees Celsius, which is 280 to 330 degrees Fahrenheit. This produces distinct flavors. The concentration of chlorogenic acid varies widely between coffee beans as well as brewing procedure. A cup of coffee can have between 20 to 675 milligrams. Quite a difference. Let's not forget about caffeine, or C8H10N4O2. Caffeine is the most widely consumed drug in the world. It acts on adenosine receptors in the heart and brain. Adenosine is the neurochemical responsible for making you feel tired. Caffeine not only blocks this effect, but produces an opposing effect, stimulating the nervous system and providing energy. Chemically, pure caffeine is a bitter, white, and odorless crystallized powder with a melting point between 235 and 238 degrees Celsius. It is slightly soluble in water, with solubility increasing dramatically with heat. The molar mass of caffeine is 194.19 grams. And using that and some concentrations found on the USDA nutrient database, it is possible to use stoichiometry to discern the difference in brewed versus espresso caffeine content. I also added a link here to one of my favorite chemists on YouTube, where he isolates caffeine from coffee. While caffeine can be synthesized using uric acid, it is much cheaper and easier to decaffeinate various products to yield caffeine. Three of the most popular methods of decaffeination are solvent decaffeination, CO2 decaffeination, and water decaffeination. Before going more in depth, here's an excellent graphic detailing decaffeination. In the US, 97% or more of the caffeine must be removed from coffee in order for it to be considered decaf coffee. Caffeine can be extracted by soaking green coffee beans in chemical solvents to remove caffeine. In the past, benzene, trichloroethylene, and even chloroform were used. These chemicals have negative impacts on the environment, and some are known carcinogens, however, so the main chemicals used today are methylene chloride and ethyl acetate. During direct solvent decaffeination, green coffee beans are steamed to open pores and then begin soaking in solvent. After soaking, the beans are steamed, dried, and roasted to remove any residual solvent. In indirect solvent decaffeination, beans are soaked in hot water to start. Caffeine and flavor compounds are dissolved in the water, which is then mixed with the solvent to remove the caffeine. Finally, the beans and water are mixed back together in an attempt to keep the flavor compounds with the beans. Unfortunately, in both of these methods, flavor compounds are lost, often making the coffee taste worse. So how can we save more flavor compounds? With caffeine extraction using carbon dioxide. That's ridiculous though, right? CO2 is a gas and can't act as a solvent. Fortunately, at extremely high pressures, over 100 atmospheres of pressure and 300 degrees Kelvin or higher, CO2 becomes a supercritical fluid. A supercritical fluid has no clear liquid or gas phases, and the CO2 takes on both properties. In this state, CO2 can act as a solvent when mixed with water. The CO2 and water mix is much more selective for caffeine over other chemicals, such as the flavor compounds, and is therefore more effective. To perform this extraction, green coffee beans are soaked in water and then loaded into an extractor. Inside the extractor, liquid CO2 is pumped over the beans. Water in separate chambers removes the caffeine from the carbon dioxide as it's circulated. Although this procedure is better for the environment and more natural using CO2, even if it's supercritical CO2, the expertise of running a high-pressure facility as well as the expense limits this method. The final decaffeination method I'm going to discuss today is the Swiss water extraction method. Invented by the Swiss, obviously, this method involves soaking the coffee beans in hot water to extract caffeine. Unfortunately, the flavor compounds are extracted again as well. However, this time, chemistry, specifically the chemical property of osmolarity, comes to the rescue. Taking the water/caffeine/flavor compound mix and running it through a carbon filter eliminates the caffeine from the mixture, leaving us with a water and flavor compound solution. Using new fully caffeinated beans, we soak these new beans in the solution. Because it is saturated with flavor compounds, most of the flavor compounds inside the beans stay, while the caffeine inside them moves from a high concentration gradient to a lower one outside, leaving the beans with only flavor compounds, thanks to nothing but the rule of osmolarity. Furthermore, because no chemicals were involved, this is a truly natural method. Each of the three decaffeination methods have benefits as well as drawbacks. Here's a table that perfectly sums up and illustrates this point. In conclusion, coffee, caffeine, and decaffeination are absolutely full of chemistry and chemical processes. So the next time you go to grab your slow roasted drug of choice, don't forget to marvel at the complexity going on within just one cup of coffee. And if it's decaf, maybe go for the Swiss brand.